Okay, good afternoon, friends, students. So today we will start third unit, uh, stresses in the beam. Okay, in which first topic is uh, the theory of simple bending. Along with, we can also learn the about the neutral axis and derivation of the formula for bending, pure bending, and also you can see, if possible, a small problem. You can see a small problem. Okay, so when a member is subjected to a bending moment and shear force undergoes certain deformations, undergoes certain deformations, the materials of the member will offer resistance or stresses against these deformations. Okay, so when any member is subjected to one force, which may be in downward direction or in upward direction. Okay, so against that force, the member will resist it against the deformation. Okay, so it is possible to estimate these stresses with certain assumptions, with some certain assumptions. Okay, so we will see the assumptions first, then the bending moments, and then we can solve one problem. Okay, so first we will see the assumptions made in pure bending. The assumptions made in the bending, not pure bending, bending. Okay, so first one is materials of beam is homogeneous. The first one is materials of the beam is homogeneous and isotropic. The materials of the beam is homogeneous and isotropic. What is homogeneous? Homogeneous means the same material is utilized throughout the member. The same material is utilized throughout the member. Okay, and second one is isotropic. Okay, means the elastic properties of the material, elastic properties of the material, elastic properties of the material, elastic properties of the material in all directions. All directions are same. Okay, so isotropic means elastic properties of materials in all directions are same, that is isotropic. Okay, so second one is beam is straight before loading and as well as after removing the loading. Okay, a beam is straight before loading and remains straight even after the load is removed. Okay, that means there is no permanent deformation. There is no permanent deformation. Okay, there is no permanent deformation. When the load is removed, came back to its original position. It came back to its original position. Okay, next third one. Beam is stressed within elastic limit and it follows Hooke's law. Beam is stressed within elastic limit and it follows Hooke's law. It follows Hooke's law. That means stress is related to strain. That means stress is proportional to strain. Stress is proportional to strain. Okay, within the elastic limit only the beam is stressed. Within the elastic limit the beam is stressed. Next, fourth one. Beam is subjected to pure bending. Very, very important. With stress to this relation only we have to derive the formula. Okay, so beam is subjected to pure bending. Okay, that means here we have to consider only bending. There is no shear stress. Okay, means we have not considered any shear stresses. We haven't considered any shear stresses. Our shear stress is equal to 0. When the shear stress is equal to 0, when the bending moment is maximum, when the bending moment is maximum, when the bending moment is maximum, okay, almost the shear stresses are equal to 0 or negligible. Okay, next, the layers at neutral axis does not take part in bending action. Okay, the neutral axis, okay, neutral axis is lies in between the top layer and bottom layer of the beam. Top layer and bottom layer of the beam. Okay, so the top layer is subjected with compression, and bottom layer is subjected to tension. Bottom layer is subjected to tension, but there is no change in the neutral axis. There is no change in the neutral axis. Okay, the length of the neutral axis remains same. The length of the neutral axis remains the same. Okay, so these are the 5 assumptions need to made in derivation of the simple bending. Okay, so coming, so we will see once again. We'll see once again. So first one is the material of the beam is homogeneous and isotropic. Okay, so homogeneous means the same material is used throughout the member. The same material is used throughout the member of the structure. Next, isotropic means the elastic properties of the material in all directions are same. Second one, beam is straight before loading and remains straight even after load is removed. Okay, so beam is straight before loading and as well as after removing the loading. It will not change. It came back to its original position. Next, third one, beam is stressed within the elastic limit and it follows Hooke's law. Beam is stressed within the elastic limit. Okay, there is an yield. Okay, within the yield limit only the beam was stressed. Within the yield only the beam is stressed and it follows Hooke's law. That means stress is proportional to strain. Stress is proportional to strain. Next, beam is subjected to pure bending. Beam is subjected to pure bending. That is shear stresses are not considered. Shear stresses are not considered. Okay, next, the layers at neutral axis does not take the part in bending action. Even the top layer of the beam and bottom layer of the beam is changing its length are subjected to some action. The neutral layer will not change its length. Okay, the neutral layer length is remains same because it is available in the middle. It is available in the middle. Okay, so these are the basic assumptions made in simple bending derivation. Okay, so theory of simple bending. Theory of simple bending. So you can see theory of simple bending. Okay, so we can take a beam which was subjected to pure bending. We can take a beam, a part of beam, we can take a part of beam which was subjected to pure bending. Okay, it means there is no shear stress. There is no shear stress. Okay, so this beam was subjected with a load of W, a point load of W. Okay, now here we can take a small strip. Okay, that means here this part of the beam is subjected to pure bending. Okay, the part length is delta x. This part length is delta x being subjected to pure bending. Okay, now here we can consider a small fiber with a length of A, B, C and D. You can consider a small part in the beam with an area of ABCD, with a stripe of ABCD. Okay, now here when the load is applied on the beam, it may deformed. It may deformed means it may subjected to bending. Subjected to bending. Okay, top part is partially compressed and bottom part is applied with tension. Top layer is subject to compression and bottom layer is subjected to tension. Okay, so top layer is subjected to compression. So this is compression. This was compressed. Top layer is compressed and the bottom layer was applied with tension. Okay, but there is no change in the neutral axis. Due to it is in the center. Okay, and here along with the beam, our small area ABCD is also changed here. ABCD is also changed, and here we are considering with respect to the neutral axis only. Okay, so the change in lengths are A dash, B dash, C dash and D dash. Okay, so A dash, B dash, C dash and D dash. Okay, now you can find the strain. For this particular area. You can find the strain for the particular area, that is A dash, B dash, C dash and D dash. Okay, so you can find strain for the area A dash, B dash, C dash and D dash. Okay, so the strain equal to initial length minus final length by final length. Sorry, initial length. Okay, so initial length minus final length by initial length. So that is, so initial length is, so we will consider with the top part. We will consider with the top part, that is CD. Initial length is CD minus final length is C dash D dash by CD. Okay, so initial length is CD, okay, and final length is C dash D dash by CD is strain. Okay, strain E equal to initial length minus final length by initial length, that is CD minus C dash D dash by CD. Okay, so here the length of CD is equal to the length of AB. The length of CD is equal to length of AB. Okay, so the length of CD is equal to the length of AB, which is also equal to A dash B dash, also equal to A dash B dash. Why? Because there is no change in the neutral axis. The length of the neutral axis remains same. So A dash B dash. Okay, CD equal to AB, which is equal to A dash B dash. Okay, only the change in the length is equal to, the change in the length is equal to, so sorry, the change in the length is occurred in C dash D dash only. Okay, now the length of CD is equal to, you have to find. Okay, the length of CD you need to find. Here CD is subjected to bend. CD is subjected to bend, means it looks like a small arc. It looks like a small arc. Okay, so for the arc, definitely we have some radius. We have some radius. We have some radius. Okay, so it is having some radius. So with a length of r, a radius of r with an angle of theta, a radius of r with an angle of theta, and here we have to consider the strip height with y. We have to consider the strip height with y, small y. Okay, the height of the y is equal to the top layer of the strip to the neutral axis. Now the length of CD, the length of CD, which is equal to AB, is r theta, which is equal to r theta, and C dash D dash is equal to r minus y theta. C dash D dash equal to r minus y theta. Okay, which is also equal to AB. Right? C dash D dash equal to r minus y theta. Now the strain E is equal to r theta minus r minus y theta by r theta. So which is equal to, so here theta gets cancelled, theta get cancelled. So r minus of minus r plus y by r. So that is, so r get cancelled here, y by r. So E equal to y by r, which is a strain formula, which is a strain. So that is equation number 1. So E equal to y by r. That is equation number 1. Now we also know we also know we also know the bending stress. We also know the bending stress sigma b by E is equal to E. E means modulus of elasticity, or you can also call it as Young's modulus. Modulus of elasticity or Young's modulus. Okay, so this is bending stress. Bending stress by strain is equal to modulus of elasticity. We can also rewrite it as sigma b by capital E, means modulus of elasticity, modulus of elasticity equal to E. Okay, sigma b by E equal to stress, sorry, strain. Sigma b by E is equal to strain. Okay, means bending stress by modulus of elasticity is equal to strain. Okay, so we can substitute equation 2 in equation 1. We can substitute equation 2 in equation 1. So equal to sigma b by modulus of elasticity. We can substitute this one in first equation. When it is substituted, so sigma b by E is equal to y by r, and we can rewrite it as sigma b by y. Sigma b by y is equal to E by r. Okay, sigma b by y is equal to E by r. So this is half bending equation. So this is half of bending equation. Okay, sigma b by sigma y is equal to E by r is the half of the bending equation, which was derived with respect to strain. Which was derived with respect to strain. Now we can consider the strip area. We can consider the strip area. Okay, this is the strip. A dash, B dash, C dash, D dash. We can consider this strip area as dA. You can consider the strip area as dA. Okay, so dA is the area of strip, or the small portion. Now from equation number 2, from equation number 2, sorry, from equation number 3, from equation number 3, sorry, from equation number 3, bending stress is equal to E by r into y. Sigma b equal to E by r into y. Now the force acting on the strip is equal to stress into area. Now the force acting on the strip is equal to stress into area. Okay, so we are considering the partial area only. So df is equal to the stress is means bending stress, sorry, bending stress into area. So sigma b into dA. Okay, now moment of resistance acting on strip is dm equal to the force acting on the beam into the strip height y. The strip height y. Okay, so dm equal to df into y. Okay, or dm equal to, we know df, it is sigma b into dA into y. Okay, sigma b into dA into y. From this is from equation number, from equation number 5. Okay, and we know sigma b equal to E by R into y. Sigma b equal to E by R into y from equation number 4. So from equation number 4, E by R into y into dA into y. So here y is available for 2 times. We can rewrite it as E by R into dA into y square. E by R into dA into y square. Okay, so dm equal to E by R into dA into y square. Now integrating on both sides, for entire beam. Okay, this is only for small area. Now we can integrating on both sides for the entire beam. Okay, that is integral dm equal to E by R into integral dA into y square. Okay, integral dm is m equal to E by R into integral dA by dA into y square is equal to I, that is Ixx. You can write it as Ixs, also you can directly write as I is the moment of inertia. Okay, so dA into y square is the moment of inertia. Okay, integral dA into y square is the moment of inertia. Okay, so m equal to E by R into I, you can rewrite it as m by I equal to E by R. M by I equal to E by R. Okay, so this is the remaining part of the bending equation. Remaining part of bending equation. So the total bending equation is sigma b by y is equal to m by I is equal to e by r. So this is the bending equation. Okay, this is a bending equation. So here we have to consider one point, that is sigma b is proportional to y. Okay, sigma b is proportional to y, means if y increases, sigma b is also increases, sigma b is also increases. Okay, so sigma b bending stress, y is the strip length, m is the moment of bending moment, I is the moment of inertia, e is the Young's modulus or modulus of elasticity, and r is the radius of the bending, radius of the bending. Okay, so for rectangular sections, y is equal. Okay, there is no change in y, but for t sections, okay, and I sections, the y may be changed. For t sections and I sections, y may varied. Okay, but for the rectangular section it is same. Now, so this equation is subjected to pure bending, that is shear force is equal to 0, but in practice bending moment varies from one section to another section, and also the shear force is not equal to 0. Definitely shear force is existing, but shear force is 0 when the bending moment is maximum. Okay, when the bending moment is maximum, shear force is equal to 0. Hence stresses produced due to the maximum bending moment are obtained from this equation. Okay, so here all the stresses are obtained for the maximum bending moment. When the stresses are obtained with the maximum bending moment, there is no shear stress, means it is pure bending and it is applicable for all beams. Okay, right. So I think the time is running. There is no time for complete one problem today. It's almost 40 minutes. So we can see the problem in next class.